Let's try a distributive practice problem. If 70.5 milligrams of potassium phosphate are added to 15 mils of an 0.5 molar silver nitrate, will result in a precipitation. Let's find a molecular equation. Potassium phosphate. Keep grabbing a pencil that's broken. Sodium is a +1. Phosphate, our polyatomic ion with a -3. Na3PO4. Being placed into a solution of silver nitrate, AgNO3 based on charge. Double displacement, silver goes to phosphate, sodium goes to nitrate. Sodium's a +1, nitrate a -1, so NaNO3, and silver phosphate, Ag3PO4. We'll need to balance with some coefficients of 3s. A 1 to 3 to 3 to 1, the way I have it written. Silver phosphate, by the way, will be our precipitate, Ag3PO4. We're given 70.5 milligrams, that's 0.705 grams of potassium phosphate. Why did I write sodium when it clearly says potassium? Easy to fix. The NAs have now become a K. Sorry. Potassium phosphate, K3PO4. 0.0705 grams of potassium phosphate are added to 15 mils of an 0.5 molar silver nitrate, resulting in the precipitate silver phosphate. Our molecular equation, a 1 to 3 to 3 to 1 ratio. What's our limiting reactant? Well, I know that I need a 1 to 3 mole ratio, and we're being asked to calculate the theoretical yield of the precipitate that forms. So what we want to know is the grams of our Ag3PO4. Let's set up a first journey where we start with 0.705 grams of K3PO4. And a second journey will be taken from silver nitrate. Our target will be silver phosphate. We can find the theoretical yield by working out two separate problems, knowing the smaller of our two answers will be the limiting reactant. So I'll need a molar mass in my first conversion of potassium phosphate. There's 3 potassiums at 39 apiece. Phosphorus adds 31 more, and 16 times 4 for the oxygen, I get 212. So 1 mole of K3PO4 would weigh 212 grams of K3PO4. The heart of our problem is a want over given ratio. Every 1 mole of silver phosphate for every 1 mole of potassium phosphate. Our want over given is a 1 to 1 ratio. To go to a gram of our precipitate, silver phosphate, I'll need a molar mass to convert out. Silver is 107.9. There's 3 of those, plus 1 phosphorus, plus 4 oxygens. 418.7 grams for every 1 mole of silver phosphate. Divide, ratio, multiply. Let's solve for this problem and see what the yield is. 0.705 grams, divide by molar mass, 212 of our given potassium phosphate. We have a 1 over 1 ratio, so I'll multiply by the target, 418.7 grams, the molar mass of silver phosphate. Maximum yield here, 0.139 grams. Let's see what we get from the other reactant, the silver nitrate. Here we were given 0.5 moles of silver nitrate per liter of solution, the very definition of molarity, moles per liter. Multiply by that volume, 0.15 liters, and we can cancel those liters, bringing us directly to the heart of our problem. We still have the same target, 1 mole of silver phosphate for every 3 moles of silver nitrate. Want over given is 1/3. Times the same target molar mass, 418.7 grams, will take us out to that precipitate unit in a gram. Molarity times liter of silver nitrate gets us to moles. A want over given ratio times the molar mass. Let's solve for the grams of silver phosphate from the silver nitrate. 0.05 times 0.015 is molarity times volume. The ratio of 1/3 times our molar mass of 418.7. 0.105 grams of silver phosphate. I can clearly see, comparing these two answers, the first answer 0.139, the second answer 0.105, the smaller of the two answers is my theoretical yield. Sometimes you hear us call it the maximum yield. It's the most I can make is the smaller of those two answers. And to answer this question, the limiting reactant is the one that gave me the smaller one. Reactants are on the left. The silver nitrate was the limiting reactant. It gave us the smaller of the two answers. Potassium phosphate is an excess reagent. Silver nitrate is the limiting reagent with the maximum yield, 0.105 grams of our precipitate silver phosphate.